Listo, cuando quieras, Max.
Bueno, buenas tardes. Good afternoon. Can you please turn on your cameras, at least for a while? Thank you. Hello. Hello, hello. Nice to see you. Okay. So, shall we start? Yes? Great. Every once in a while, an astronomer comes up with a great idea. We scientists, as you may know, are sometimes overconfident and maybe a little bit too much enthusiastic. So we start thinking about, for example, nature publications, or we start planning a trip across several countries to give invited talks and show our results and receive some prizes and so on. But after the eureka moment and after the dreaming moment, the job has to be actually done. So if you're the person who had the idea and you think this is a great idea, then you commit yourself to make it very seriously this time, and you proceed like follows. The planning for the project. The first step is to call for a team meeting. In a team meeting, you invite every person that will be eventually involved in the project, including, for example, the emeritus professor who will bring the money, the topic group who knows very well the theoretical foundations, the IT department which will be giving support to the software development, some students which will produce thesis works related to these projects, and so on. In these meetings, you also analyze the viability of the project, how possible is to carry out this idea, how possible is to make it happen. And for that, you need some resources, you need some experience, you need some data, you need a lot of things. So in many cases, it is possible that the project cannot be done with the resources that you have at hand. But let's suppose that you conclude that the project can be done. So you analyze the funding sources, not just the present funding sources, but the future also. Because you need to buy computers, for example, you need to acquire books and to travel abroad and so on. Then you consider the different talents in the team and you assign the roles accordingly. So each person can feel comfortable in its role within the project. And then you make a schedule from the very first day to the end of the project, or maybe to the end of the first paper, or maybe to the completion of the thesis of the PhD students. And every steps which are necessary for the project are written down and are put in a table so that everybody knows what happens and when it should happen. So you can even make a schedule to measure if you are on schedule. Okay? Well, does it sound familiar to you? If it does, raise your hands. Not your actual hands, but the icon hand. Yes? 1, 2, okay. Some of you feel familiar with this situation. Very good. What about this alternative scenario? The idea, the great idea, is explained to a PhD student twice. If you're the student and we all have been there or will be, then you barely understand a few words of what's going on. But at least you have clear the first steps in the process, which are, in the first place, try to figure out how to grab some data from somewhere. You will be the only person which will be actually working in the project. And there are other people that you have to report to, right? So it is very important that you make your work on time, on schedule, even when you do not have a clear idea of what's the end of the project, right? Once you have some data, you see what happens. That's the second step. See what happens means make some plots. And you have to be sure that you will plot anything before your thesis advisors comes into your office, or the excitement for the project goes. What happened first? And the excitement goes on average after 24 hours, more or less. So you have to plot something very quickly. Then you have to write code to make the plots, to analyze the data. The situation is different if you are working on the observational side, on the theoretical side, doing simulations, doing data analysis, etc. So you will have, for sure, to write code. And then you will have to make some clever visualizations. And maybe after all that process, you will write a paper, but it is not very clear at the beginning how many papers, what these papers will be about, and so on. And you do not have very clear also what is the relation between this project and your thesis work, right? So I presented two very different scenarios. I would say that one of them is closer to the ideal, and the other one is closer to reality. From your point of view, the second scenario looks more familiar than the first one. Yes, hands? No, Matthias, not your actual hand, the icon. Okay, thank you. Well, this situation happens a lot of time. So the question now is, how is it possible to work more efficiently? And I will argue that it is possible to produce more and better work in less time or with less effort. We just need to get more organized, okay? Some time ago, I read a book called The Ninth Revelation. Do you know the book, The Ninth Revelation? If you know the book, please take it into account that I was young and I didn't know exactly what I was doing, but there was something interesting in this book that the character was having realizations during the book, 9 revelations, which, well, led him to some situation. But I think that in the research work, from time to time, one discovers a thing with a feeling that I wish I knew this before, right? Because you discover something that is very useful, and using that thing, you can make your work better, faster, okay? So I will tell you about 9 revelations that I had in my career so far, okay? Not the 9 today, but at least I think 5, and the other ones in the next session. The first revelation is that you already know it. You have the feeling, you feel it from the deep of your heart, and the feeling is that you can do better. We all make a great effort, right? But sometimes it feels like this effort has no relation with the results. So the first revelation is the most difficult one, because once you embrace this idea that you can do better, maybe changing something, maybe changing the attitude, maybe changing the tools, maybe changing the methods, maybe changing the results, the resources or the opportunities. We need something, okay, which allow us to do things in a better way. So once you accept this situation, you can do something about it, right? So this is the first revelation, that we need something else to work better. The second revelation is not very obscure. It is something very simple, that you need to work in an organized manner. You need, for example, make a directory tree which is useful for your project. Things to take into account in order to build this tree. For example, you can use any scheme. Any scheme is okay, as long as you use it and maintain it. If you are changing the scheme all the time, then it is difficult for your collaborators to follow what you're doing. Okay, so it is very useful to think through at the very first day of the project, how will you organize your files and your directories? This is not a waste of time. This is very useful and very important. This organization, this directory tree, should be communicated or shared or documented for your collaborators, so that everybody knows where are the files, how to access it, and so on. For example, the most common strategy is to make the codes in some Git repository and and put the data in a cluster, for example, or in the cloud or whatever, right? Use intuitive names. That means not folder 1, folder 2, folder 3, but the folders should have a name which actually reflects what they contain, and the same for files. There are many frameworks, for example, a language called Rails, and Django, and Kotlin for writing code for Android, and so on, that generate a directory structure with files and many things. You can use, if you use one of these languages, you can use these frameworks. But if you're using, for example, Fortran or C++ or R or Python, then it is not quite easy to get a framework to generate this structure. And all of this is part of the so-called data governance criteria, which means you have to establish the names of the files, the names of the directories, who is accessing what and when, and etc. There is a basic distribution of directories, for example, data and source. This is very basic, but something better is that is when you create a documentation directory, a directory for tests, and a directory for notebooks, because notebooks are a different thing from the code that you are using to run your experiments. Most of the time, I will be thinking about Python, but this is relevant to any language. Even better than this, it will be possible to create some subdirectories or directories within the other directories. For example, for raw data or for the product, which are two very different things. Then in the source, you can consider, for example, the extract, transform, and load process, the ETL, or the EDA, the exploratory data analysis, mostly if you're using a project from data science. The models can be anything. Most of our projects involve some kind of model. And also documentation, notebooks, and tests. There is a tool called Cookie Cutter, which allows something similar to the tools, to the frameworks that I mentioned a minute ago. Using this, you will have a standardized way to create a directory tree with licenses and README and a lot of things. Let's try it. Okay, you can try it in your terminals if you want. This is using Python, so it is better if you create a virtual environment just for this activity. Okay, let me bring I'm sorry, just let me change the appearance. Okay. Now, I am within a virtual environment called FoF. You can see the mark here. And the first step is to install this tool, the Cookie Cutter. Simply pip install Cookie Cutter. Okay, very fast, very easy. And then you write Cookie Cutter, and this direction with this a direction in a GitHub repository with a data science structure. Okay, so you put enter. There are a series of questions that you will have to answer. Are you trying to reproduce this exercise? You can, if you want. So the first question is the project name. Okay, let's go, for example, for test. Okay, the repository name, your name, Marcelo, a description, the default option is okay, a license, for example, the one MIT license. You can use the S3 service from the cloud. If you're not using it, which is the most common situation, just put enter. If you're using Python, choose your interpreter, and that's it. As you can see, there is a new folder here called FoF test. It wasn't there before. If you go into FoF test, here at the right, you have the contents of the highlight folder, right? And you can see all this structure has been created by Cookie Cutter, Okay, data, external, engine, process, and raw. A documentation folder with some initial configuration. An empty folder for models, an empty folder for notebooks, an empty folder for references, reports. Maybe if you're writing a paper or a thesis or some other kind of report, it will be here. And the source, and for the source, you have a data directory, features if you're working in a machine learning project, models and visualization. This is a proposal. Okay, you can change it at any of its parts. But the important thing is that anything you do is very well organized. Okay, and a README is always very useful for that. The requirements file, which tells which packages are used for the code. And this is prepared if you want to make a package out of the Python code. So this is a little tool that could be useful for creating a directory structure. This is the result. We saw it a moment ago. So I recommend it to try it, and more importantly, to keep the structure that you feel is more useful for your project. The next revelation is to organize the tasks and the time. There are a lot of tools that can be used to organize these things. For example, I can mention these 4 tools. We have Trello, for example, Asana, Jira, and this is a little screenshot of Google Spaces, which comes with every Google account. These 3 tools are meant for different sizes of project. For example, I think that Trello is the simplest one. Jira is the more complex one. And Asana is my favorite. And Google Spaces is also very useful because it comes with your mail. So you have chat and meet and mails and tasks all in the same place. This is an example of a screenshot from Asana. I've been using Asana for a while. Vanessa, one of my students, is also using it, and she likes it. She likes it very much. So this is a very good option. And the other thing is the organization of bibliography. I am aware that all the things that I'm talking about maybe are very basic, but the organization, the organizers of the meeting asked me to tell some of these things. So if you think it is very easy, or you already know everything, please tell me and we go faster. Okay. So these are 2 tools to organize bibliography. There are many more, but the important thing is that you have to organize the bibliography that you will use in your project from the very first moment, not at the end when you're going to write the paper, but from the day one. Okay, and these tools are very useful to do that. And finally, you have to use an IDE, integrated development environment, which suits very well to your needs. So there are many IDs. It's just okay if you choose one of them, any, as long as you can use it and you can leverage all the properties of this tool. Okay. Some are meant for complex projects, for example, PyCharm. Some are very simple, for example, this one, which is called Thony. You have Sublime, VS Code, Notepad for Windows, Atom, and Vim, for example, all very good IDEs. The next revelation has been version control. Once you understand the possibilities of version control, you get surprised of why you weren't using it before. That happened to me at least. Version control has many tools, mainly SVN and Git. Today, Git is a more popular tool. For example, if you use GitLab or GitHub, are based on Git. And there are a few commands that you need to know in order to use this version control. And it is very useful because if you change something in your project and you need to go back to a previous version of the code, you can do it using this tool without the need of replicating many files with many versions of your code. And this is very useful also for other things that I will show you in a minute. The next revelation is set everything up. Because the situation, which happens a lot, is that you write some code, you run experiments, and then you change parameters. It's all we do is changing parameters all the day. So when you change parameters, how can you be sure that you will know exactly what are the results and what are the plots and which is the data corresponding to each piece of code, right? So one possible strategy is to use setting files. This has been useful for me. Maybe it's not for you, but I think it was a try. Right? There are many formats for making configuration files. For example, the ini files, the XML, the YAML files, and the JSON files with different characteristics, with different wrappers to read and write these kind of files. All of them are human readable. Some are easier than others. The data to markup ratio is high in the ini files and the YAML files and the JSON files, but it's very low in XML. This means that you have a lot of writing, but the actual data is a small fraction of it. The disadvantage of the ini files is that you cannot use nesting variables, but you can do it with the other formats. Let me show you some small examples of what it looks like. The XML format uses these bracket things, so you can read it, but it is not very comfortable. Okay, and you have to open and close every sentence. The ini files are a bit more clean, I think, because you just use the name of the variable and equal sign and the contents. The contents are always strings, but you can convert to a float or a number or anything in case you need it. The JSON format has a lot of brackets and parentheses and square parentheses and all kind of parentheses and so on. And the quotes, which are also a little bit confusing or not, I don't know. But for me, this is not as easy to read as this format, for example. And finally, the YAML, which is, I think, similar to the ini files, with a high content to markup ratio also. And the advantage of YAML files with respect to the ini files is that you can make nesting, okay? You can make variables within variables within variables, right? So how can we use the settings files? You can make your code to run an experiment, and instead of hard coding the parameters, you know what hard coding is, when a parameter is written down directly in the code, right? Instead of doing that, you can put all the parameters which are changing or will eventually change in a separate file, settings file, and then your code is always the same file without changing, and the only thing that changes is the settings file. Okay? I will show you an example in a little bit. And the final revelation for today is reproducibility. I will spend more time with this. The life cycle of the data science project includes, for example, experimentation, reproducibility, ufa, elegí una palabra difícil. Deployment, persistence, meaning that you have to save the files and access them again later, and trackability, meaning that you need to know every data file and every plot and every result, where does it come from, okay? Which code, which parameters, which criteria, etc. Right? These are very important aspects of the data science life cycle. But if you're not doing data science, if you're doing, for example, simulations, or if you're doing observations or analyzing observations or reducing observations and so on, then this is also important, okay? This is important for any kind of project. Some strategies that I find useful, for example, use configuration files, save everything, and you may be thinking, okay, I cannot save everything because it is a lot of memory, a lot of volume. Well, there are some smarter strategies to save what is important, okay? You need a very strict governance, meaning the directory tree that you set up in the first stage of the project, the Git repository, the number of the files, the number of the directories, everything has to be very clear, and if possible, written in a document. Okay, it can be a PDF document, or a report, or part of the thesis, or anything. Okay. Anticipated change means that you need to put in your settings file everything that you think can eventually change. Okay, so that you do not need to go to the source file of the code and change things there. Okay, and many times you will have to do, for example, if-else structures, because you will need to code decisions for your project, and that's okay. Maybe the code is a little bit longer, but the code is always the same, and everything is set up in the configuration file. And here's the discovery I made. I learned about this working outside academia recently. So I want to show you because I think it is very useful. There are some tools or services or program or whatever called project managers generally, but more specifically metadata stores. And these are the names of these tools. For example, Neptune, Weights and Biases, Comet, Valohide, and MLflow. MLflow stands for Marcelo Lares. No, it's for machine learning. Because all these tools are designed to improve the machine learning life cycle. However, they can be used for any kind of project, and I will show you how to use one of these tools for a project which is not for machine learning, right? So let's see some strategies to improve the persistence and the trackability and the reproducibility and so on. Let's say we have an experiment which is in a function in Python, okay, called experiment, right? Then we can do the following. There are some packages for Python, for example, sys, os, and pathlib, which are very useful because you can, for example, get the working directory, right? And write down all the path that you're using so that if you change from your machine to another machine or to a collaborator machine or to the cloud or anything, then the code will be working all the time, right? If you write down, for example, an absolute path, that is not possible. Another thing is that you can set up for a name of each experiment. Okay, for example, let's say that I make a function experiment with an argument which is the name of the experiment. So each time I run this function with this name, a set of files and directories and configuration files and anything are produced by the function. For example, you can check if there is a directory called output dir. This should be run name, okay? I made a mistake. Let's suppose that the argument is run name. So we want to know if there is within data a directory called run name with the value of the variable run name. Okay? Do you understand? Yes? So you should put here run name outside the quotes. And if this directory does not exist, then you can create that directory within the program. So this is useful because every time that you run the experiment with a different name, a different directory is produced, and maybe you can save in that directory plots and data files and so on. Okay, for example, we save in the just created directory this new file that we computed in our function. And there is the final strategy using, for example, a metadata store. I will show you, for example, with MLflow. And it is very simple. I will stop here for a moment because this is the most important part. You can import from MLflow some useful functions which allow you to log or to save a metric, for example, a parameter, or artifacts. Artifacts are mainly data files or plotting files, right? So for example, you can save here in the parameter named param1 this number. It's just a random number, it doesn't matter. And you can also save in this metric foo, for example, this value and this another value and another value, right? So you're saving for the experiment all these values, and these values will end up in a table, which is very easy to read. I'm going to show you in a moment. You can also generate data files or plots or whatever and save them using the log artifacts function, right? So 3 functions, very easy. And you can automatically track the experiments you are performing, right? So let me show you how to use MLflow for a project, which is a data science maybe project, but not a machine learning project. I will share with you a link, okay, from a GitHub repository, so you can download the code I'm going to show you, right? Tutorials. I'm using a folder structure produced with cookie cutter, right? And in notebooks, I created a notebook with an experiment, which is representing the first step of a research project. So let me open this notebook, which is called Core Func, right? You have it in the repository. So we open the notebook, and I will explain briefly what I am doing here. So the project is compute the correlation function in the catalog of galaxies. We are all friends of the correlation function. So we are going to make this experiment, right? Here are a few words for documentation. An index you can use, for example, in Jupyter notebooks. This trick using cross-referencing, like LaTeX, for example. And how you do it? You make this. Maybe it's a little bit small. It's better now. So this is the trick. You create a link, okay, with an ID, a link of nothing, right? This is HTML code. I created, for example, the link noise, and then I use hashtag noise here. So if you click there, you go directly to that section of the notebook. I show you this because I think it is very useful, because notebooks are very long typically. So if there is a way that you can organize it better, it's a good thing. Now this experiment works with the correlation function, which I am using the correlation function, the 2-point correlation function from AstroML package, right? So let's see first the correlation function of random points, I mean white noise, right? We generate white noise, and we run this just in case. Generate white noise, compute the correlation function, and we can see it. The correlation function of white noise is supposed to be close to 0, right? Now let's plot something. This is the correlation function of white noise, right? It's all close to 0 with a tolerance of 0.02. We can compute the uncertainty bars in the computation of the correlation function with the boosted 2-point function, right? Very easy. And here we have the plot of the correlation function and the error bars. And now we are going to do the same with a Galaxy catalog. So I have two files that I downloaded previously of the luminous red galaxies in Sloan, data release 7, right? If you read the fix file with the table tool, then you can see something similar to a pandas data frame. Okay. You can plot, for example, the redshift distribution for the galaxies and for the randoms. There are two files, a file for galaxies and a file for randoms. We need the two in order to compute the correlation function. If we don't have, for example, the exact mask and footprint of the catalog. So first, let's filter a little bit. This is the footprint of the random catalog and the galaxy catalog. There are much more randoms than galaxies, right? We can take a redshift range. Here's the filter. No, I'm sorry. This is the galaxy catalog, and this is the galaxy catalog in the redshift range. And this is the random catalog, and this is the random catalog in the redshift range. You can see some structure here for the galaxies, but not here for the randoms. So the next thing is to select a region, like here, more or less. And we are computing the correlation function in this small region. I am doing this so that the experiment can run very quickly. Right. Okay, let's transform the coordinates into redshift space coordinates. I did it in a function. I generate with gem space a set of values of distance where I want to compute the correlation function, and that's it. It has already run. And here's the result. Okay, the correlation function of luminous red galaxies in Sloan. A very easy experiment, maybe an exercise from a course in astronomy. But what I'm going to do now is to reproduce this same experiment with different parameters and with different options and with a lot of experimentation. And I'm going to save all those experiments. Okay. So in order to do that, let me open a different file. Source. I will open C runs here. This file is also in the repository. It is very small, right? Better? This is okay? So this is the same thing, but it is in a file. And I also implemented the settings file. Here is the settings file. I made it with the ini format. Okay, so we have the experiment and the parameters for the experiment. For example, the experiment series, I call it FoF. The experiment ID, I use 3 letters usually. For example, those letters that means something only for me. A random seed, the relative range, the alpha range, the declination range, the range of distances in order to plot the correlation function, the number of pins, the estimator, which can be standard or Landis-Alai, and the parameters of the cosmology. Okay, so we can read all these parameters with a tool called config parser here. This package, config parser, allows you to read an ini file and get all the parameters. So I did it like this, but you can make your own function, or you can do it in another module or something, so it doesn't use so much space. And then you end up with all these variables which are taken from the configuration file. It is very simple, just 2 lines. You create an object of the type config parser, and you give the number of the file. You can pass the number of the file from the command line also if you want. And then we made the same thing from the notebook, right? Read the data files, make the filter. I go very fast with this. If you have any questions, just ask me. We set up the cosmology, and there is the possibility to change these values because these values are present in the settings. Okay, here. Maybe we are going to change them. Maybe not, but it is a good thing to anticipate the change. Okay. We set up the name of the experiment. I will delete this line. The name of the experiment series, which is FoF, and the name of the run, which is this one. And there is a function that I made, this function getRunName, which is a very simple function. You gave it the name of the experiment, and this function returns the name plus a number. Okay. So, for example, for the first experiment, it will return L theta D 001, next L theta D 002, and so on. Is that clear? I can show you how it works if you want. So this is the experiment. It's very simple, right? Transform the distances to commobile distances. Compute the relative space coordinates, and compute the 2-point correlation function here. Then save a file called crcsv. It's a comma separated value file. Then make a linear fit to the function, because maybe you want to see the parameters of that model. Okay. We make a plot, right? And we save a set of parameters. We save a set of metrics. Do you remember the 3 functions of MLflow: log param, log metric, and log artifact? And we save also some artifacts. For example, the plot, the file with the correlation function, the file itself, which is running this experiment, okay, and the settings file. You can, if you want, say less than this or more even, I don't know. So let's run, this experiment for several configurations. The first time that you run this file, a directory called mlruns here will be created, and within mlruns, there are a series of directories where all the artifacts and the parameters and so on are saved. But it is better than that. Just trust me for a moment. I will delete this directory. So there is no mlruns directory, and I will run this experiment. Okay. First, I open the virtual environment. Core func, source core func. Here we are. This is the directory we were before. And with the Python version of this virtual environment, I will run this experiment. Right. So as it says here, the folder with the FoF name does not exist, so a new one is created. Right? There is a new file here, a new folder, mlruns, and within mlruns are some contents of the experiments that we made. But the best thing is that we can track the experiments with an easy interface, which works on a browser, an internet browser. You can do it MLflow user interface. Also, you can do MLflow server, right? And then it opens a location here. So click here, and here's the set of all the experiments that we are making, right? The FoF series, and within the FoF series, the LZD experiment, and here's the data, the settings file, the data for the correlation function, the plot with the fit of the model, and the code we use to produce this plot. So we have everything here. And since it is sometimes difficult to organize all the data files and all the settings files and all the copies of the code and so on, this interface allows us to have all these in a single page. Now we will change some parameters. For example, I will choose 10 here, maybe. I run the experiment again. What is this? The Jupyter notebook. Sorry, let me go back to the directory source or func. So Python C runs again. Do you remember the message that there was no FoF directory, so it was created? This time there is no message because the FoF series already exists. Let's make a couple more of experiments. Maybe I make here 0 and 40. I don't know. We change something, right? And make another run. And after that, I will change the Hubble parameter from 65 to 70 and run just another experiment. So we have a few experiments for now. And we will load this page. And here we can see all the experiments, right, with different names, LZD, 0, 1, 2, 3, right? And in each case, we can see a description, we can add it. The parameters here, those are the parameters that we used for the experiment. The metrics, which are the parameters of the linear fit, okay? The plot, for example, and so on. The code that generated that plot, the data, everything is here. For example, if we want to compare two experiments, right? We can see which are the parameters that changed. For example, between these two experiments, the Hubble parameter changed, but the other parameters were the same, right? And this is how the metrics, for example, here we see the Hubble parameter, we changed from 65 to 70. And here we see the slope, no, the intercept of the fit. We could use the slope, for example. The slope is more or less the same. No, the slope changed, okay, changed to these values. I don't know if you can see, for example, 3 experiments. Okay, here you have 3 experiments, and you can compare what changed from one experiment to the other. Okay, and in each case, you can enter the specific experiment and get all the parameters for that experiment. So it is very easy once you understand the basics of how to set up this. But if you use this tool from the very first experiments, then at the end of the project or at the end of your thesis, for example, you will have a very long list of experiments, and all of these experiments are easily reproducible, and you can track every plot, where does it come from, and so on. I think this is very useful because of all the experiments that you make in your thesis, for example, what fraction do you think will end up in that infamous table in the thesis work? I would say, I don't know, 2%, 5% at most. But the vast majority of experiments are not written down in the thesis, okay? There are many experiments that you do and they are lost in the ether, right? So I recommend this tool so that you can register, track down, and reproduce any experiment you make in your work. So the code is in the GitHub repository. You can check out, you can try by yourself. If you have any doubt, you can contact me anytime. If you have any question right now, you can also ask. This will be, from my part, everything for today. So do you want to ask something? Any complaint? Sí, Rafa. Technical problems.
Hello.
Yes.
Hello, Marcelo.
Yes, I can hear.
I'm using Rafael's computer. I wanted to ask, this file that contains all the information of all your runs, all your simulation, is it a heavy file?
it depends on what are you saving into them. For example, in this case, ML runs is 1/2 of a megabyte. But we made some simple experiments, and we save a few metrics and a few parameters and some plots, and that's it. But of course, if you run thousands of experiments, and for each one you save many plots and large files and so on, this will be a large directory. You can also copy this directory into another machine, into another folder anywhere. And if you install the MLflow package, you will open the same page that we are using here. Exactly the same page, right? There is a possibility, there are many possibilities. One of them is to save the results not in your local folder or in your local machine, but into another machine. For example, you can run the experiments in your laptop and save the results in the cluster, for example. Or run the experiments in the cluster and save the results in your laptop. Or run the experiments anywhere and save the results in the cloud, for example, in Google or Amazon or whatever. And also you can delete experiments. For example, if you just click one of these and delete, it is gone, right? So if an experiment has not a very useful result or is not very nice, you can delete it. But the drawback of that choice is that you will not have a register of the fact that you made that experiment and the result was not very good, which is a result also. Matthias? Matthias says, at which point do you employ MLflow in your project? Once you have an apparently functioning main program on which to test different parameters, or even before starting the main program? Well, actually, you have to write a functioning program before running your experiments. So you can track the experiments for the development phase, but it is perfectly possible, but maybe the results are not so useful for the research project, right? But they could be useful for tracking the evolution of the software, for example. I don't know. It depends on what do you need. I don't know if that answers your question. So another question. Well, I hope de nada, Caro. I hope this was useful for you. I tell you, it was very useful for me. I have been using some of these tools for a long time. Not MLflow, which I learned very recently, but for example, Asana, Git, and many things I have been using. Even if you feel that you are wasting your time by creating organization, which is not actual research, right? At the end, it is worth the effort, because there are many problems that will not happen if you work in an organized manner. right? Okay.
Okay. Thank you very much, Marce.
You're welcome.
And that's all for today. See you tomorrow.
Gracias.
Gracias a ustedes. Adiós. Bye bye.